Howdy. This video is on equilibrium constants. Understanding equilibrium is essential for understanding chemistry. The first 4 chapters of Chem 114 are just on equilibrium. To be able to determine concentrations at equilibrium, we need to be able to understand equilibrium constants. Many analytical techniques are based on equilibrium systems. After watching this video, you should be able to write expressions for Q, Q sub C, K, and K sub C for reactions. You should understand the differences between Q, Q sub C, and K sub C, and understand when Q equals Q sub C and when K equals K sub C. You should understand that when a reaction is multiplied by a number, the new equilibrium constant is equal to the original equilibrium constant raised to that power. You should understand that when the products and reactants are switched, the new equilibrium constant is equal to the inverse of the original equilibrium constant. And you should understand that when 2 reactions are added, the equilibrium constant of the new reaction is equal to the product of the original equilibrium constants. So we've seen these equations previously. Delta G naught equals minus RT natural log K. Now remember, these two are constants for a specific reaction at a specific temperature. They're independent of the concentrations. And delta G non-standard equals delta G naught plus RT natural log Q. So delta G non-standard and Q change as the reaction proceeds. Delta G naught standard change in Gibbs energy is a constant for a specific reaction at a specific temperature. Now for both delta G naught and delta G, we can actually calculate using products minus reactants. Now for delta G naught, that's when you have pure products minus pure reactants. And so again, it's a constant for a specific reaction at a specific temperature. Now delta G is actually the slope of this line. And so for the minimum, the slope is 0. And so at equilibrium, delta G is equal to 0. And so at equilibrium, delta G equals 0 means the free energy of the products and reactants are equal at those concentrations. To calculate delta G for the free energy of the components, you have to be able to calculate the non-standard conditions. And so the non-standard Gibbs free energy is equal to standard Gibbs free energy plus RT natural log A, where A is referred to as the activity. Now, activity is a little confusing. For an ideal gas, the activity is just equal to the partial pressure of the gas divided by 1 bar. And so that makes the activity unitless. For an ideal solute, something that you add to a solvent, the activity is equal to the concentration of the solute divided by 1 mole per liter, making that unitless. For pure solids and pure liquids, the activity is just equal to 1. So in this class, we typically deal with gases at low pressure, relatively low pressure, and temperatures high compared to the boiling point. Hence, we'll always be able to assume ideal gas behavior in this class. We'll also deal with only dilute solutions, hence we always make the approximation of that the solute is ideal. Now in more advanced courses, organic, analytical, physical, you may not be always make that assumption, and you'll see that the activities are not just going to be equal to the partial pressure or the concentration. And for solids and liquids, sometimes you'll see the activity is not equal to 1 if you're in more advanced courses. And so in Chem 112, we discuss ideal gases and ideal solutions. Activities are used to take into account non-ideal behavior of gases and solutions. The higher the pressure, the less the gas will behave ideally, and the bigger the difference between activity and the partial pressure. But again, in this class, we are dealing with just ideal gases and ideal solutions. And so the activity of a gas is just equal to partial pressure divided by 1 bar. Activity of solute is equal to concentration divided by 1 mole per liter. And activities of pure solids and liquids are just 1. So what is the molar Gibbs free energy for glucose at 0.25 molar concentration at 25 degrees Celsius? Now again, standard conditions would be 1 mole per liter. And here we have 0.25 moles per liter, and so that's a non-standard condition. And so our non-standard molar Gibbs free energy is equal to standard molar Gibbs free energy plus RT natural log A. We can see in the appendix that the standard molar Gibbs free energy is minus 917. We're assuming ideal solutions, so our activity is 0.25. We're at 25 degrees Celsius, which corresponds to 298 Kelvin. And we do the plug and chug, and we get that the molar Gibbs free energy non-standard is equal to minus 920. And so we can look at the reaction. We have 2NO plus O2 goes to 2NO2. Now again, we saw that even for non-standard Gibbs free energy, we can do products minus reactants. And we saw the expression for our molar Gibbs free energy. And so we plug in the expression for our molar Gibbs free energy here, here, and here. And so again, this is non-standard, this is standard, and then this is the activity. And so now if we plug in this stuff for the molar Gibbs free energy, we get this. Now notice that we got standard Gibbs free energy here, here, and here. Now if we take those out, we'll see that's equal to delta G standard, right? So you got that, and that will give us delta G standard. Now we got RT natural log A and RT natural log A, and so we can combine those terms, and so the RT comes out. Natural log A minus natural log that. So the 2 can actually go inside the natural log, and so that becomes natural log A squared. This 2 goes inside, so natural log A squared. And so this equation will be on the top of the next slide. So we got this. And so natural log A plus B is equal to natural log A times B. Natural log A minus B is equal to natural log A over B. And so we can go from here to here. Now, trying to cool, what you should notice is that this has products over reactants, coefficients become exponents, right? NO2 is our product. NOO2 are our reactants. We have a 2, that 2 comes down here, that's 2's over there. And so this is actually where products over reactants, coefficients become exponents came from. And so that's the same as, remember, reaction quotient, Ekman constants have the same form. Products or reactants, coefficients become exponents. Now notice that because we're dealing with activities, that means this is unitless. And so all Ekman constants, all reaction quotients should be unitless. Now this is just equal to our reaction quotient, Q. And so that gives us delta G equals delta G naught plus RT natural log Q. Now remember, at equilibrium, delta G is equal to 0, and Q is equal to K. And so that gives us 0 equals delta G naught plus RT natural log Q. And if we subtract RT natural log K from both sides, we get delta G naught equals RT times the natural log of K. And so we have this reaction. We can write down the Ekman constant this way. Products of reactants, coefficients become exponents. And we should remember that, for a gas, the activity is just equal to the partial pressure of the gas divided by 1 bar. And again, that coefficient becomes that exponent. Now it's acceptable to write down the Ekman expression as just this way with just the partial pressures, as long as remember that this is the same as this and it's the same as that. We could also write it in terms of concentrations. And so when you see a K sub C or Q sub C, it means it's in terms of concentrations. And remember, for activity for the concentration, it's the concentration divided by 1 mole per liter so that it is unitless. And so we can write it in terms of concentrations. Square bracket means concentrations, moles per liter, as long as we remember that this means that, and Ekman expressions are unitless. So for the reaction, our K would be in terms of activities, and so we end up with this. Our K sub C is in terms of concentrations, and so we have that. Now they're both Ekman constants. One's in terms of activities or partial pressures, and the other is in terms of concentrations. And one question we could ask is, do they have the same numerical value? And what we'll see is that for this reaction, they do not have the same numerical value. So if we want to determine the numerical relationship between the two, we can start by remembering, okay, the partial pressure is equal to nRT over V, where N is the number of moles, R is the gas constant, T is temperature in Kelvin, and V is the volume. So if you plug in this for our partial pressures, we get this. And then if we take the N over V's out, keep the RT's, and then we see, okay, N over V, N over V, N over V. Those are just concentrations, right? So N is moles, volume is liters. and our concentration is moles per liter. Now this RT squared cancels this RT squared, and we're left with 1 over RT. Now if we think about our K sub C, that's concentrations, products or reactants, coefficients become exponents. And so you notice that this is right here, and then you left with the RT. And so K equals K sub C divided by RT. And so that's why the Ekman constant in terms of activity is not always equal to the Ekman constant in terms of concentrations. And so what we'll see is that K equals K sub C when you have the same number of gas particles, products, and reactants. And so K equals K sub C times RT to the delta N, where delta N is number of gas particles products minus the number of gas particles reactants. And so looking at our reaction, we have 2 gas particles products. We have 3 gas particles reactants. That gives us a -1. So our delta N is a -1. So we get K equals K sub C RT times RT to the -1 power, which is what we actually found before, that K equals K sub C divided by RT. But we can use this equation here if we ever want to know the relationship between K and K sub C. And so again, K equals K sub C only when you have the same number of gas particles, products, and reactants. I should also notice that sometimes there's confusion about this reaction. This reaction only enables you to determine the relationship between K and K sub C. It does not tell you the temperature dependence of the Ekman constant. So sometimes there's confusion because you have temperature here, but it's just that the relationship between K and K sub C is temperature dependent. We can look at another example. And so here we have 2H2O liquid going to H2 gas plus O2 gas. And so in terms of activities, we would have the activities H2 times activity O2 divided by activity H2O. Now again, pure liquids have activities of 1, so do not appear in properly written Ekman expressions. In terms of gases, we use the partial pressure, and as long as you remember the partial pressure is equal to the partial pressure divided by 1 bar, we actually can lead out that 1 bar. So you just have to remember this is the same as that. So this is our K. Now we can also do our K sub C. Now the only difference really in writing an expression for K and K sub C is how you treat a gas. So if you're writing K and you're looking at a concentration, you still write down the concentration. If you're writing K and you're doing a gas, you do it in partial pressure. If you're writing K sub C and you're looking at a gas, you still write it as a concentration. And so the only difference in how you write the K and K sub C is how you treat the gases. And so for our K sub C, we treat everything in terms of concentrations. Our liquid, we still have just activity of 1. And so we can write down this as long as you remember that the concentration is divided by 1 mole per liter. So the Ekman constant is unitless. And so this gives us our Ekman constant, and this gives us K sub C. And we can ask, will these be different? And numerically, they should be different because, again, you notice that you got 3 gas particles products and 0 gas particles reactants. If we do that derivation again, we see that K equals K sub C times RT to the power 3. Again, we could just use this equation, K equals K sub C times RT to the power of delta N, where delta N is gas particles products minus gas particles reactants. And so you get 3 minus 0 gives us 3. And that gives us K equals K sub C times RT cubed. And again, remember that K equals K sub C only when you have the same number of gas particles, products, reactants. And again, this equation does not tell you the temperature dependence of Ekman constants. It's just that the relationship between K and K sub C is temperature dependent. So we can look at some more examples. So here I have H2HCl aqueous going to H2 gas plus chlorine gas. So our K, we write the gas in terms of partial pressures. We write the aqueous in terms of concentration. Our K sub C, everything is in terms of concentration. Only difference between how you write a K and K sub C is how you treat the gases. the relationship between K and K sub C. So K equals K sub C times RT to the power of 2. Because again, delta N is number of gas particles products minus number of gas particles reactants. And so both K and K sub C can be used to describe the most stable configuration. If you use K sub C to describe the most stable configuration, you have to use Q sub C. If you use K, then your x-axis has to be just Q. And so K in the following equation, when we're using delta G equals minus RT natural log K, this K always has to be the K written in terms of activities. You cannot use K sub C in this equation. If we look at another example here, we got silver chloride solid going to silver ions plus chloride ions. And so again, for K, in terms of activities, the aqueous are in terms of concentration. Pure solids, pure liquids have activities of 1, and so are not included. K sub C in terms of concentrations look exactly the same. Again, the only real difference between how you write a K and K sub C is how you treat the gases. In this case, because we have the same number of gas particles on either side, 0, that means K equals K sub C. And so a question you could be asked in the very near future is, what is the relationship between K and K sub C for the following reactions? And so again, K equals K sub C times RT to delta N. And so here we got 2 minus 1, so that would be delta N of 1. And so K equals K sub C times RT. Here we got 3 gas particles, and so K equals K sub C. Here we got 11 gas particles and 9, so 11 minus 9 gives us 2, and K equals K sub C times RT squared. Again, be careful, you're only supposed to be looking at the gas particles. Here we got 1 gas particle, and so again, K equals K sub C times RT to delta N. So for this first reaction, delta N is 1. Here we have 0 gas particles, so K equals K sub C. And here we have 0 gas particles, so K equals K sub C. Determine K sub C for the following at 1,000 Kelvin. And so we're given K. And so K equals K sub C times RT to delta N. And so we got 2 gas particles products. And we got 3 gas particles reactants. So our delta N is equal to minus 1. And so that means K equals K sub C divided by RT. And so K sub C, if we multiply both sides by RT, K sub C is equal to K times RT. And we are given our R is 8.3145 times 10 minus 2 liters bar mole Kelvin. Our K was given as 3.4. And our temperature is 1,000, and so we get, well, we'll get an answer. But one confusing thing is, I thought K was unitless, and so it is a little confusing. When we write this, we actually mean the activities. We actually mean the partial pressures are divided by 1 bar. When we write the concentrations, we actually mean the concentrations divided by 1 mole per liter. And so when we write K sub C equals K divided by RT, what we actually mean is K sub C equals K 1 over RT times 1 bar over 1 mole per liter. And so if you notice, for your R, it's in liters bar mole Kelvin. It has to be these units to cancel with the mole and the bar. And so in this problem, we get 4.04 times 10 minus 2. And so for this type of problem, you have to make sure you use the right value for R. Again, it's a little confusing because, when we write one thing, we actually mean something slightly different. K's are always unitless. And so we write down an Economic expression for this. Again, it's just products over reactants. This is a K sub C. Now, if we swap the products of reactants, so we put the SO2 gas as a reactant, if we put this as a product, if we write down the new one, the new Ekman constant is going to be the inverse 1 over the old Ekman constant. And so that makes sense because for this reaction here, you notice your K is really large. So that means the products are more stable. And at Ekman, you have mostly products. If you flip it, now our Ekman constant is really small, means that the reactants are more stable. And so if you swap products reactants, you take the inverse of the Ekman constant. If you multiply a reaction times 2, you have to square the Ekman constant. And so this is the Ekman expression for this reaction. Now if we multiply this reaction times 2, now this is our new Ekman expression. Again, coefficients become exponents. And so you see the new Ekman constant is equal to the old one squared. And so the value for this Ekman constant is 1.1 times 10 to the 62nd. And so if you square it, you get 1.2 times 10 to the 124th. If you multiply a reaction times 4, and so chemical reactions are like mathematical equations. You can multiply through by a number. And so if we multiply through by 4, we go from 1 to 4, 3 halves to 6, 1 to 4. We have to take the old Ekman constant to that power, to the power of 4, to get the value of the new Ekman constant. Now if we add reactions, so again, chemical reactions are a lot like mathematical equations. You can multiply through by a number, you can add them. And so if we add these two reactions, we get this reaction down here. You notice that things common on both sides cancel, so the SO2s cancel, and we're left with this. Now if we think about the Ekman expressions for that first reaction, we have products over reactants. Pure solids, pure liquids don't appear. So this is the Ekman expression for the first reaction. Ekman expression for the second reaction, we have SO3, SO2, O2 to the 1/2. Now, if you add reactions, you multiply the corresponding Ekman constants. And so if we multiply this times that, the SO2s cancel. We'll be left with SO3 divided by O2 to the 3/2, which is going to be the Ekman expression for that bottom reaction. And so if you multiply through by a number, you have to take Ekman constant to that power. If you flip it, then you take the inverse. If you add reactions, you multiply the corresponding Ekman constants. And so if the top one had an Ekman constant of 4.2 times 10 to the 52nd, and the second one was 2.6 times 10 to the 9th, then the sum is going to be 1.1 times 10 to the 62nd. Given the reactions corresponding to Ekman constants above, what is the value of the Ekman constant below? And so sometimes you'll have to manipulate these reactions. And so if we look at it, we got 2BrCl, 2BrCl. And so we probably don't have to change that top reaction. Now we got 2HCl, and we have 2HCl as a product here. And so we'll probably have to flip this reaction. So we're not doing anything for the first reaction, so it doesn't change the Ekman constant. We're flipping the second one, and so we have to take the inverse of the Ekman constant. Now when we add these, we'll get the reaction we're looking for. And when you add the reactions, you multiply the corresponding Ekman constant. And so the Ekman constant for the reaction we're looking for was 2.5 times 10 to the 9th. We can look at another example. And so using these reactions and Ekman constants, we want to find what is the Ekman constant for this reaction. And so we have HClO here. We have hydroxide ion. And so the second reaction, I think we'll keep as the same. The first reaction, we're going to have to flip. So the first reaction, we flip, and our Ekman constant goes from being 1 times 10 to the minus 14th to 1 times 10 to the plus 14th. The second reaction, we didn't change. We add these reactions. We'll get the reaction that we're looking for. And notice that the hydrogen ion cancels because it's common on both sides. And when you add the reactions, you multiply the Ekman constants. And so if the reactions multiply by a number, you have to take the Ekman constant to that value. If a reaction is flipped, you have to take the inverse of the Ekman constant to get the new Ekman constant. If you add reactions, you multiply the corresponding equilibrium constants. And again, please remember, typically K is in terms of activities and K sub C is in concentrations. The only difference really is how you treat the gas. For K, you treat the gas as a partial pressure. K sub C, you treat the gas still as a concentration. The relationship between K and K sub C, K equals K sub C times RT to the delta N, where delta N is number of gas particles products minus number of gas particles reactants. Remember, activities are unitless, and so equilibrium constants are also unitless. I hope that helps.